Hello everyone, today we are going to start the third unit of the song, which is the bending stresses. So far we have seen the tensile as well as the compressive stresses, but apart from both of these stresses we also have a third type of stress, which is known as bending stress, and such type of stress occurs in the beams due to the bending. So if certain shear force and bending moments are applied on the beam, then there will be certain deformation in this, so it will try to bend, and the resistance to such type of bending will induce a certain bending stresses in such type of beam. So that is known as basically the bending stresses. So if we just move into a more concise definition of the pure bending and simple bending, then we can understand this via this example, in which we have such type of overhang beam and W load is being applied at the exterior ends. In this case you will find that this is SFD and this is BMT diagram. So in this case you will find that at this portion there is no any shear force acting, and consequently the bending moment at this section is known as bending moment of magnitude minus WA. So such type of cases in which no shear forces are acting on the beam, but certain stresses gets induced in it, these are known as basically the bending stresses. And for that there are certain assumptions in the theory of this simple bending, that these are the 6 assumptions. Let's say we have to assume that object is homogeneous, the value of Young modulus is same as in that in the tension and compression, so and the radius of curvature is also large compared to the dimension of its cross section. So these are the following 6 assumptions that you must remember if that is asked in the examination. Next, in order to derive the bending equation, so we have we will just try to just derive that bending equation. So for that we will consider this to be a section from this section from the middle section, which is in a state of a pure bending. Okay, and we have two sections, that is AB and CD, and this is the neutral axis at which no tension and compressions are there. Okay, so when the load is being applied, so after the bending, its shape is like that, where this A dash C dash is the fiber which is having the compression, and this B dash D dash is the fiber which is in tension, and this is the neutral axis which is neither in tension nor compression. So these two cases will be there. So if we just look into the derivation of the formula, then we will find that we will suppose that we have a fiber of length EF at a distance of F, and this is the radius of curvature, and this is the theta angle. So and this is its stress diagram, and which is showing that the top fiber is in compression and the bottom is in tension. So this is the stress diagram of its top and bottom fiber. Okay, so if all of these things are given, if we suppose that this this EF is equals to delta x, very small, this is will be equals to NN, that is neutral x, that is delta x. Okay, so from here we will calculate the equation of that is strain equals to y over r. So from these two equation we can say that NN dash equals to r theta. As you know that solid angle and plane angle, so if we say what is solid angle, then solid angle is theta is equal to L over r. So if we use that equation, then we can determine the value of NN dash, which is r times of the theta. Okay, so this is basically a solid angle, that is theta. Similarly, we can find out the value of E dash F dash, and that will be equals to this value. And similarly, the increase in the length in this fiber EF will be difference of this, which is equals to y theta, and the strain will be equals to strain increase in length over the original, that is y over r. So this is the strain in this fiber YF, this is the strain that gets developed. Similarly, if we just find out the stress at a distance y in any fiber, so we can use this equation to find out that stress, which is equals to the stress equals to E by E over R into times of R, and just if you just work out in this formula, then we will get this formula. Okay, now in order to derive the bending equation, we need to just incorporate here M and I. Okay, so in order to do so, we all need to understand what is the moment of inertia and what is the bending moment. So if we know both of these terminologies, then we can easily incorporate both of them. So let us consider this section area of dimension dy and area A at a distance of y from the neutral axis of this rectangular section. So the force which will be acting on this layer will be equals to stress into the area, which is this formula, and if we just integrate it for the whole section above the neutral axis, then we will get this formula. And when we know that since this is a case of pure bending, so net shear force will be equals to 0. Okay, so in that case this can't be 0, and then this will be 0. That is why times of into d equals to 0, and this is defined as the moment of the area about the neutral axis which coincides with the centroid. That's why it's equals to 0, and this is denoted by I. Next is moment of resistance. So how we are going to just define this moment of resistance? Okay, so if we consider about this pure bending case where no shear force is acting, then the above layer will be in compression, below layer will be in the tension forces. So these stresses, due to these stresses, there will be obviously force that will get developed on these layers, and these forces will have, obviously if that's force, then that will have a moment around this neutral axis, that is 4 times of this neutral axis. So that from where we can get, so if we just add all those moments about these forces about the neutral axis, then that will give the moment of resistance of that section. So if we just, so this is the force stress times of the area. If you want to find out the moment, multiply by y. So this equation gets reduced to this form, and if we just want to find out the moment, then we will just integrate for the entire section, and this equation gets reduced to this. And if we consider m to be an external moment, and that is being balanced by this moment which is induced inside of the beam, and since this is equals to I, and hence this equation gets further reduced to m over I equals to E over R. And if we just work out on this, and we know from the previous formula that sigma over y equals to E over R, just put the value over here, then you will get m over I equals to sigma over y equals to E over R. And this equation is known as bending equation, and we will be using such type of equation in order to solve our numerical problems. And this is one of the very important formula in the strength of material, and you will be using this quite often than not. Okay, and in the next video we will be studying about the section modulus of rectangular and the circular section, and then we will just wrap up the first half of the third unit. Okay, thank you.